John here. Let's wrap up our discussion on how we would implement, design and implement a CPU. In this case, let's target the RISC-V, the RV32I instruction subset of the RISC-V processor. This is a block diagram of an entire CPU that should be able to execute any of the RV32I instructions. Let's look at the various components. The yellow ones in this diagram you should recognize. We've seen all these before. The ALU, these are multiplexers. This is our register file that we looked at before. We saw the innards of this. These multiplexers are drawn using a style that we talked about before as well. These multiplexers, rather than having single bit inputs, have whole buses coming in. These fat blue lines, as drawn in this diagram here, represent 32 bits of data. Okay, that's indicated by these names on these buses. So the name of this bus right here that comes out of this D latch, right? This is an edge triggered D latch. You see the triangle right there. It says D in and D out. That's overwhelmingly obvious. That's a D latch. And the name of it is PC. So guess what this is? This is the latch that holds the value of the program counter. The output of this latch is called PC. It has 32 bits and so on. So each one of these fat blue lines should have a name of some kind. IMM_X, for example, to name this bus, is so named because this box here generates the 32-bit sign extended value of any of the IMM values that come out of the instructions. All right. The X here is used because it represents the value of any one of them. If it's immediate for an I type or a U type or a B type instruction, all the immediate values are encoded differently inside the instruction. It is the responsibility of this white box here to take as inputs the value of the instruction bits itself, and in that it will look at the opcode value, right? Because that's what determines the instruction type. The instruction type determines whether or not it even has an immediate value, and if it does, the particular type of format that immediate value might have. This thing will react to that and generate the 32-bit value of the immediate operand as its output. Okay, this is left as a task for the viewer/student to figure out how to build such a thing. The short of it is you can use multiplexers to do this kind of thing. All right, so inside this white box here would just be some multiplexers, and the address input of that multiplexer would be the instruction opcode field itself. Okay, what else is going on here? There's the ALU we're familiar with. This particular ALU, I've added some extra functions to it. It has a function control we've already seen, the subtract and shift right arithmetic, but the subtract aspect of this, we've discussed it in some detail in the past. This is the extra bit when the ALU is adding. When you set this bit here, it will convert the adding operation to a subtraction operation by complementing the inputs and setting the carry in of the full adders that are within this ALU. We discussed that before. What I have not discussed before is the operation of shifting values. Let's just assume that, shifting is just yet another combinational circuit that has a truth table. You can work all this out by hand, and it should come as no surprise that you can implement a shifter using a large number of multiplexers. So let's just assume this ALU does everything we've talked about in the past, plus it can shift, and the amount that it shifts is given by this shift amount input field here, and you may recognize that because it is one of the things that comes out of the immediate field for the shift immediate instructions. And these are the bit positions that we're concerned with for how far we need to shift. We'll talk more about that later when we look at some instructions. These new things here are just more outputs that I've added to this particular ALU that become true if these two A and B inputs are equal. If A is less than B in a signed comparison, this little U right there indicates that this is A is less than B in an unsigned comparison. And the way you do this is pretty straightforward. You simply tell the ALU to subtract the two items. If the answer is 0, they're equal. So that's easy enough to do. If you put the ALU into subtraction function mode, or however you want to call that, and you just put an OR gate in there that ORs all of the output bits that come out of the Q output here together, If that value is 0, you know that they're equal. So you put a NOR gate on there to generate this equal signal. To compare a signed value, to ask if A is less than B in a signed comparison, in the simplest case, you can subtract them from each other, and if the result is negative, if they're both positive numbers, obviously, if A is less than B, then you'd end up with a negative result. There's a couple of combinations. What if A is positive and B is negative, or B is positive and A is negative? Things like that you can work out a truth table for, and again, you can work this out by looking at the sign of the result and the sign of the two input bits and work together a truth table to figure out the circuit that you need to do this. Similarly, if A is less than B and the two operands are unsigned values, this one's a little bit easier since they're always positive. So you simply ask if you ended up with an unsigned overflow as a result of subtracting B from A. And when that happens, you know that A had to be less than B, okay? These are all just little logic puzzles that can be solved with truth tables and some combinational circuits, okay? More multiplexers. We see multiplexers all over the place in here. And again, they are all bus-style multiplexers. In other words, input 0 is 32 bits. In this case, it comes from the register file. This multiplexer here can be used to select whether or not the ALU A input comes from what is the RS1 register in an instruction, or it can instead be used to propagate the current value of the program counter into the ALU A input. All right, the same kind of thing goes on the B input. We'll see all this when we look at some of the instructions. The B input of the ALU can either be RS2 or it can be, as you can see, this line wraps around to the immediate value. So if I were to do an instruction like add immediate or something, and I wanted to add an immediate value to the value of the RS1 register, it would make a certain amount of sense that I have to have a way for the value of the RS1 register to flow into one of the inputs of the ALU and the immediate value to flow into the other input to the ALU. So you can see ALU A select and B select over here are used to determine whether or not the ALU is operating on the value of two registers, which is what happens in the R-type instructions, or if we're operating on the program counter and immediate value, or a register with an immediate value, and so on, all right? That's what that gets used for. We've talked about the register file at great length in another discussion. Here's another multiplexer whose job it is to determine what the RD register value uses in those instructions that actually have a destination register. You know, if I'm going to add two registers together, for example, it makes sense that you have an RS1 and an RS2 value. Those would flow into the ALU. The output of the ALU would flow out and around down here in this line and back up into this multiplexer. So if I said add two registers together, RS1 and RS2, and I would store them in the RD register, okay, it would have to have some way of connecting this output of the ALU back into the register file in order to complete that operation, okay? Other instructions that we would look at, like if you're going to load a value out of memory, there needs to be a way to grab a value from our memory component down here. Whatever's coming out of the memory, it has to be able to also flow up and into the destination register, okay? So if we're going to add registers together, we need to be able to, you know, get the output of the ALU to go into the destination register. If we're going to load from memory, we need to be able to get the memory to go into the register. That's the purpose of this mux over here. We'll also see that if we execute the jump and link or the jump and link register instructions, there needs to be a way to store the program counter into a destination register as well. So we see some fancy stuff going on to handle that over there. This white box over here, as I've labeled MBRSX, this thing handles the sign extension that is needed for the loading of bytes and half words out of memory that have to be sign extended before they're stored into the RD register. Again, it's a white box. I'll leave that as a task for the viewer or student to determine what's in there. Surprise, it'll be some multiplexers, okay? This will have to know the size of the operand it's getting out of memory. It'll also have to know something about the alignment of the data that's coming out of memory as well in order to do this properly. So I've allocated enough bits to this signal here to allow what we'll see down here, the control finite state machine, to tell this thing what to do, okay? So that leaves us with this multiplexer down here and the big finite state machine box down here. Let's look and see a little bit about how the memory works when we're writing data into it. Now, this is a memory block that we've discussed at some length before. It has the ability to write data into it. It actually has a dual ported bus. It is an input bus and an output bus. And we're going to just simply connect the read and write addresses together like this. So whatever the memory is doing, it's always going to be reading and writing at the same address, okay? So what happens in here? If we think about the RV32I instruction set, the only way to store any data into the memory of the machine is to use one of the S-type instructions, the store instructions, of which there are 3. There's a store byte, a store half word, and a store full word. Okay? The only data item that can ever be written into memory has to come from the RS2 register in those instructions. Now, as you will see, this bus here moves its way around like this and grabs onto the RS2 output of our register file. Okay, so that's just permanently wired onto there. If you're ever going to write anything into memory, it has to only come from the RS2 register. Okay, and that seems reasonable because it's the only instructions that we have to do that. Whenever a memory clock has a rising edge on it, it will cause the data that's on this bus to be stored into the memory at the address given in the address bus right here. Again, I'm leaving out a discussion on how memory alignment works and what happens, for example, if I were in a byte to an odd numbered address and so on. Surprise, there should be some multiplexers either explicitly in a circuit here or part of this memory block over there in order to make that happen, to align the data to where it belongs in the 32-bit value that gets written into the memory, okay? This is busy enough. I'm going to leave that as a task for the student to ponder and contemplate that on their own. This multiplexer here can be used to determine whether the address that goes into this memory that controls which, what values we're going to be reading or writing at any point in time can either come from one of 2 sources. One of the source, when adder cell is 0, is the output of the ALU over here. So the ALU can calculate the value of an address that we can use to interact with the memory. The other way to do this is the obvious way. It comes from the program counter. Most of the time, we'll find out that the program counter is the thing that needs to go down here and become the address of the memory so that we can read instructions from the memory, all right? Now, when stuff comes out of the memory, when the program counter is flowing down here like this for the address, those are generally going to be instructions. We have an instruction register in here to hold those values. Whenever INSIN clock over here has a rising edge, this is a D latch, it will grab a copy of whatever's on the data bus coming out of the memory and latch onto it and propagate it out the INSIN bus over here. The instruction bus is used, as I discussed earlier, to deal with calculating the current sign extended immediate value that may or may not be part of the instruction that's stored in this register. And it also flows down this bus here into this finite state machine down here. Okay, so that's pretty straightforward, and it's block diagram view. I would argue the yellow parts are well within our grasp. The white ones can be figured out by combining a number of multiplexers together. And that leaves us with this big box down here, the control finite state machine. It should make a certain amount of sense that the equals and the A less than B inputs from the ALU have to be involved at times in determining what this finite state machine will do. In particular, they're used for conditional branch instructions, and they're used to determine whether or not the program counter will advance to the next instruction by adding 4, or the program counter can be loaded by the result of a mathematical operation that adds either, an immediate value to a register or immediate value to the program counter, depending on which instruction we're dealing with. We'll talk about that a little bit later when we talk about the branch instructions and jump and link instructions, okay? The rest of the inputs for the control finite state machine have to deal with the opcode, the func3 field, and whether or not this special bit is set in what is the func7 field that we discussed before. It should make a certain amount of sense that what we need to do is control these clock signals here based on the current instruction that's being executed right now. For example, does the instruction have a destination register at all? Right? If it does, eventually this state machine would have to put a rising edge on the destination register clock field, for example. All instructions ultimately will update the program counter, so it's just a matter of when and what value the program counter should have, whether it's a branch instruction or just simply going to the next instruction and so on. All instructions get fetched out of memory, so eventually we have to load them into the instruction register, and that's these various clock signals, all right? These select signals, I already talked about ALU A select and B select. We'll see there's a number of these. These connect to all of the multiplexers that are in this design and drawing, okay? What those are there for is, depending on the instruction, we need to know whether or not, for example, the B bus of the ALU should be consuming the value of the immediate operand in the instruction, or does it consume the value from the RS2 register that might be part of the instruction. Same thing with ALU A select, right? Well, let's look and see a little bit closer about the program counter itself. Now let's look and see what's inside this blue box here and take a detailed analysis of what's going on. At the heart of it, we see the program counter register. D-latch, it's got the PC clock sitting here. Every time there's a rising edge on this signal here, the program counter will be given a new value. That new value comes from the output of this multiplexer over here called U17. The control on this multiplexer is called PC next select or next cell, okay? When next cell is a 0, the input to the multiplexer that comes from this bus over here will be sent over to the program counter. Whenever the next cell is a 1, the input comes from over here, which you might recall wraps around down here and comes from the output of the ALU. So what does that really mean? It means that the program counter, whenever we want, can either be loaded with a value from the ALU that might be calculating some mathematical operation on some registers or something, like in the target of a branch instruction, or it can come from this adder over here. And we mentioned this before. You can put a separate little adder, a mini ALU that only knows how to add, for example, and it can know how to add something from this multiplexer to the program counter value itself down here. Now, what do we have as options for this multiplexer? Well, one of the options is just the number 4. If you have PC ALU select set to high, input 1 will propagate through this multiplexer here, all right? And whenever that is the case, current program counter will be added to 4, and this PC ALU bus will have the value of whatever the current program counter is plus 4. And we'll see that this is the general way that we use. This is what we'll call a data path, okay, that goes around this circle here, and how we're going to continuously increment the program counter by 4 in order to keep pointing it to the next instruction when the time comes. So if PC ALU cell is always a 1 and PC next cell is always a 0, then every time PC clock has a rising edge, we will add 4 to the program counter. We can just do that forever. And we can, in that case, use that to execute any number of instructions as long as there's no branching, okay? When there's branching involved, we need to do other things. Like, for example, maybe we need to add the current value of the immediate operand in the instruction to the program counter instead of just 4. Okay, that would allow you to branch to an to an address relative to the program counter. And as we saw before, the branch instructions and the jump instructions have program counter relative addressing. Okay, so one way to do that would be to take the program counter and set PCU ALU select to 0, and then be able to add whatever the current immediate operand is to the program counter, and then load that in the program counter. Okay. Another way we can do that is through this other path down here. If you look closely, the program counter can also be sent up and around into the regular ALU up here. And if we wanted to, we could do the same thing. We'd add the immediate value to the program counter using the ALU. And that output of the ALU could come around over here, come back up and around there, and input of the mux over here. And if PC next cell is a 1, that could then be stored in the program counter. So we actually have two ways to do that same function. All right. It turns out sometimes it's better or more efficient, I should say, to use the ALU to do the operation. And other times it's more efficient to have its own little ALU over here. And I'll leave it as a task to the reader to optimize this if they want to see if they can get rid of one or the other and speed up the processing of instructions or reduce the cost of this particular design. This has not been designed to optimize anything other than the minimization of what we need to discuss to execute these instructions, okay? So bear that in mind as we move forward. So let's start with this blue box and move on to the timing diagrams that show how we make use of what's in this box. Now, ignore the stuff down here. Let's just look at what happens over the course of time if we want to just execute a number of instructions that don't involve any branching. From what we just talked about in that loop, that is the program counter, the two multiplexers, and that adder. Let's look at this timing diagram here and see how it all relates. If the PCU ALU select is high. Remember, that was the case that put the 4 into this multiplexer here. Okay? PCU ALU select is high, then this 4 goes in here, and then this adder, U15, will always be calculating PC plus 4 at all times, and therefore PC ALU should always have the value of PC plus 4 on it. Now, we can see that is, in fact, the case. I've arbitrarily decided that, at this point in time, T0, we will assume that somehow the program counter ended up with a 0 in it, okay? And because PC ALU select is high, PC plus 4 is what's going to be outputted on the PC ALU bus over here. And you can clearly see that that is a 4 right there. Now, because the PC next select here is low, as I said earlier, it will propagate the PC ALU bus output into the program counter register right here. Like I said before, PC next select is low, input 0, which is the thing from that adder. All right, given all of that, if there's ever a rising edge on the program counter clock signal, the input, which we know is the value from PC ALU due to this down here being low, will be latched into the program counter. So what we've done here is we've built a circuit. Granted, it's somewhat convoluted for this simple task, but when PCU ALU is permanently tied high and PCU next select is permanently tied low, and the clock is ticking here, every rising edge, as you can show from this cause effect arrow down here, of this clock causes the PC register to be loaded with the current value that's on the PC ALU bus. So it'll count by 4, 0, 4, 8, C, 10, and 14, and so on, in hex, of course. And anytime this value in the program counter changes and is updated, the PC ALU will also react and continue its adding of 4 to whatever is on the program counter. So once you change the value of the program counter from 0 to 4, you end up seeing right away the output of the ALU reflecting 4 plus 4 in hex, which is 8, okay, and so on as we go along. So this right here, we're going to build on this and use this to fetch our instructions. All right, now let's move on to look at what happens if all we want to do is just fetch some actual instructions. Let's look at some code like this. These instructions here, let's assume, are stored in memory at these addresses over there. If you scroll to the bottom of this picture, this one's entitled Fetch and Decode Cycles of U-Type, R-Type, and some of the I-Type instructions. I consider these to be the more easy ones to understand. Let's start with these first, okay? So this diagram, let's make sure we all know how to read it. I'll put links to the diagram below the video if you're on YouTube and you want to find this and follow along. Some of the type is pretty small. You might not be able to see it if you're watching this on a phone or something. Okay, so if you've got these various instructions up here, and they're stored in memory at the given addresses here, you'll notice these addresses here are what we just looked at going by up here in the example of the program counter advancing itself over time. You can see I've simply copied that part of this diagram down in this larger image. What we're going to see here is all I'm doing is adding more to the same diagram. Okay, so this is the same thing plus more stuff. What that stuff is in this case are these instructions as encoded like this. And what we're going to see is what we do with the program counter, how we get the values, and how we decode them using the circuit we were just looking at in the block diagram of the CPU. Now, I've done us the courtesy of doing excessive labeling in this diagram to show you this is the period of time when the Louis instruction up here at address 0 is executing. Okay, and you look at the bottom, this is T0 times 1 and time element number 2. Every 2 cycles of this clock, we're going to see one instruction will execute based on the design in the block diagram. You can design other kinds of CPUs. Maybe they can execute one instruction every clock cycle, or maybe some instructions run in 1 clock cycle, other ones run in 2, and so on. One of the merits of the design that I chose to use is that all of the instructions that we're going to look at can execute in 2 cycles based on that design. So it kind of simplifies all these diagrams, okay? So each one of these pairs of clock cycles, and a clock cycle is represented by 2 waves of the clock signal here, all right? I'm going to label with the instruction that's being executed at that time. And you'll see these are the order that you see them on in this code here. These comments over here show that if I were to execute this instruction based on the knowledge we have of the machine, what the state of the registers are, and so on, this is what the machine would do. And we're going to see these values and how they're used in this diagram down here, okay? So what then's going on? Let's look at just the Louis instruction. Now you remember that the Louis simply takes whatever you've given it here, and in hex it would add 3 zeros to it, okay, and store that value in the destination register, all right? So let's take a close look at Louis X15 with hex 8, all right? What do we know? We know the opcode, if you look closely in there at that instruction, is a 37 in hex. These gray areas in this diagram down here represent values that, while we could know what they are, they're utterly irrelevant. Remember, the Louis instruction does not have value in these bits, which represents the func3 field. It doesn't have a func3 field. Therefore, these bits, we don't care what's in here in terms of reacting to that field as a func3 like we do in add immediate and shift right immediate and so on. That those have func3s, and that those bits become relevant to these instructions. Now, of course, these bits are used, but they're not used for a func3 field, right? Same thing with bit number 30. This is only used, remember, when we're dealing with shift right, whether it's arithmetic or logical, and whether we're adding and subtracting and stuff like that. So we'll see over here when we're shifting, that is relevant, and when we're not shifting or adding, it is not relevant, okay? Now, I know you say, oh, I'm adding here, but remember, it's the R-type add instruction that has a func7, and bit 30 is used, not add immediate. There is no subtract immediate instruction. I'd mentioned that in an earlier lecture, okay? Now, back to the Louis instruction. We've got a destination register. It makes sense that we have an RD value that is 15 in decimal here, right? Because remember that the register numbers are in decimal when you write them out like this. And the RD signal, these names here match the schematic drawing, right? So RD, for example, is these bits out of the instruction, and in parentheses, oh, by the way, that's the RD field. That goes in, represents the right address of a register we want to store data into if there is a subsequent rising edge on this clock over here. So it makes sense that there would be a 15 on that RD bus at that time when there's a Louis instruction running for X15 as its RD register number. We already looked at the clock and the ALU select and all these lines in here, the program counter related stuff. And you can see that it's going along very nicely. Program counter is currently 0. All right, notice it changes halfway through this instruction. We'll talk more about that a little bit later, but that's okay. It's not a problem. Now, continuing along here, we have the instruction register clock signal here, and we see the value of the instruction register on these two lines, right? And I've drawn a cause-effect line here showing that when the instruction clock goes high is when the instruction register itself gets loaded with a value from somewhere that we'll see is down here. It's related to the memory signals, okay? When the instruction register has been loaded during these two clock periods, the value of the instruction register is the instruction that's being executed at that time. And we can see the value here, 000087B7 is exactly the instruction encoding up here from the source. All right, so this really is a Louis instruction running for 2 cycles. And that is defined simply by the fact that the instruction register has that value in it for those 2 clock cycles. All right. Now, the Louis instruction has no RS1 or RS2 field. The bits that would be used for RS1 and RS2 don't matter, so I have them grayed out again, all right? It has an immediate field, the 8, remember? And it has to be sign extended to the left and 0 extended to the right in order to form the value that we want to store in the destination register. Okay, so it makes sense that the IMM X boss would have that value on it during this instruction. Now, the address select line, as I mentioned before, if all we're going to do is fetch out instructions from the memory, it's always going to be high, which means, and I've added these little helpers in here so that I don't say the wrong thing, by the way, and it should help you to remember that when address select is high, that is the MUX address input that selects between the program counter and the ALU, right? That's the signal on this MUX down here, right? Do I want to send the program counter down as the address into the memory, or do I want to send the current value coming out of the ALU down as an address into the memory? Unless we're executing a store instruction, or we're loading from an address that's not in the program counter, we want to use the program counter for all of our interactions with the memory, especially for these instructions, because they don't ever use the memory for any other purpose. Now, you'll notice these are all half gray and half white. Let's look and see what's going on here. The value down here, because it propagates through the MUX from the PC, it has the same value as the PC. All right? Again, as long as this stays high, the PC will propagate through that MUX and come out on the memory address field down here. And the value that is in the memory at this address will then ultimately flow out of the memory output bus here. Okay, and what is stored at address 0? Well, that is going to be the instruction encoding for a Louis instruction. So let's see what's kind of going on here. So for one time period, for one clock cycle before the instruction executes, the program counter address has to be sent down to the memory and the value fetched out of the memory. That happens one clock cycle before the instruction register can know what came out of the memory. Right? It takes time for all this to take place. So we send down the program counter, we wait for the memory to send us a value back, and after a little while it has passed, we can then have a rising edge on the instruction register clock input and load what's coming out of the memory into the instruction register at that time. This takes time, is the point. Now, the fact that it's half white and half gray is because what matters is the value that's coming out of the memory up to and including the point in time where we have this rising edge. We talked about this before. It's the speed of light situation. It's why the program counter actually counts, right? What's coming into a register matters before the clock edge rises, not after. So I've purposely added these gray areas to show that while we know what's coming out of the memory during this time, we don't really care what the value is between T1 and T2. And we'll see that this will make a difference later on in some of the instructions. What matters is the value on the memory bus just before and during the rising edge of this clock, not what's on there after, okay? And we're going to take advantage of this for some instructions, is where I'm going with all that. So early warning on that, okay? So what happens here for this Louis instruction? This all should make sense at this point. We need to make sure that the destination register is 15, and that's easy because some of the bits right in this instruction are labeled RD. If we go back and look at the encoding in the fields of the Louis instruction, right? What do we got? We got an RD field, we got the opcode field, and we have the immediate operand over here. Okay, so it makes sense that we can just simply take bits 7 through 11 and connect them directly up to the register file as the RD register, as we've done in here. If there is an RD and we are going to clock a value into the register file, that destination register will be given in these bits right here, period. No matter what, okay? Same thing happens with RS1 and RS2. It's okay if these have garbage values on them when we don't care what's flowing out, for example, an RS1 value. If this field here has bits in it, like it does in a Louis instruction, Louis has no RS1 and it has no RS2, okay? But it does have bits in these positions. It'll turn out that the register file will react to those bits and it'll start outputting values. It doesn't matter what's coming out over here because when we're doing a Louis instruction, as we're going to see, we don't care what's on these buses because the ALU will not be using the data on these buses. It'll be using the program counter and it will be using the immediate value over here to calculate the value that it needs to store into the RD register, okay? And we'll see all that on the next page. So the act of fetching the Louis instruction and decoding the values that are relevant in the various fields of this instruction are illustrated then in this graph. Now, why are these things staggered like this? All right. Well, they're staggered because if I want to execute the Louis instruction in these two time periods here, I need to get the Louis instruction into the instruction register, and it has to be held in there for these two clock periods. In order to get it in there, I have to fetch it out of the memory. I talked about that a minute ago, and it has to be stable and valid during the rising edge of this clock. After that point in time, I can prepare the memory system as soon as I want to, even all the way over here, to get ready to start making the value for the next instruction, which will be this one over here, making it available as an output from the memory for the next instruction, okay? So this is sort of staggered. We update the program counter a little bit early so that we can get the next instruction loaded when we want it to be, okay? We have 2 clock cycles to do whatever work we need to do for any instruction, all right? Part of that work includes incrementing the program counter to point to the next instruction and getting the memory ready to give it to us so that we can fetch it on the rising edge of the next instruction clock. All right, so what happens over here? AWE-PC, we have X2 is the destination register, so it makes sense to see 2 over here in the RD field. The opcode extracted from AWE-PC is a 17 in hex. Clearly you can see that over here. The 1 in here represents the destination register X2. Remember, there's an extra bit that it steals out of this byte down here when you decode an instruction, right? So the binary value is actually 2, even though when you print it out in hex as a 32-bit number, there's a 1 sitting up there, okay? So what else goes on with the AWE-PC, right? Well, we have an immediate value here. And the difference between Louis and AWE-PC is that when we do an AWE-PC, we add this immediate value to the program counter and store the result in X2. And when we do a Louis, we simply sign extend and 0 extend the operand here, and we just store that in the destination register, okay? So the difference is that there's an addition going on here. Now, when it comes to fetching and decoding these 2 instructions, that's not particularly relevant yet, but it will be when we start looking at how we execute them, all right? So keep that in mind. Otherwise, the fetching of these things and getting the immediate value ready and stuff like that are the same for both of these 2 instructions. So that part of the system is identical, right? What do we do if we have an add immediate instruction? All right, well, let's look up here to make sure we know where we're going before we get there. There's the instruction. It's at address 8, and we should be able to see that an 8 was in the program counter over here, and we'll look below and see that that's what the value is that we fetched the instruction out of to get this opcode 13, which is, again, hiding in this 9-3 there. If you think that the high order bit, remember, is used as part of the register number, this is what's left is a 1-3. So that's why the opcode of the add immediate, as coded here, is a 1-3. The func3 field now comes into play because all the I-type instructions use the func3 to tell which kind of I-type instruction that we want to execute, and the func3 bits from 12 to 14 are used to represent the func3, and I just put in here that, by the way, those bits represent the add immediate function. I could just put the binary value in there, but it might be more useful to know what the binary value means. You can always look it up in the RVLP document of what all the fields mean for the different instruction types. Because we're doing an add immediate, as I explained earlier, there is no need for the func7 field. In fact, it doesn't even have a func7 field, right? So again, whatever happens to be in bit number 30 is not relevant with respect to concerning ourselves with whether we're adding or subtracting or shifting logically in arithmetic. So what happens then down there? Okay, so again, we have the X1 register in the instruction, and the bits that represent the RD field will have the 1 in it, so I show that in here. We already talked about the program counter clock. We've already talked about how the instructions are fetched and everything else. This all lines up and matches in all the other instructions. Remember, the add immediate has a destination register, it has an RS1 field, and it has an immediate operand, okay? So it should make sense that you'd see an RS1 field that has a relevant value in it for this instruction, and that's a 2, because the register number 2 is the RS1 register number. The 10 immediate value, once it's sign extended, becomes the hexadecimal value A, all right? Moving along, what do we got? A shift right arithmetic immediate. Now we care about the func7. Well, I call it func7, but in the shift right arithmetic immediate operand, if you go back and look at the RVLP, or shall I say, if you actually go look at the official RISC-V in documentation, these are still I-type instructions, all right? It doesn't really have a func7 field over here, but because the shift amount can only be 5 bits of information, what we do is we abuse the fact that this I-type instruction only uses these 5 bits for the shift amount, and we sneak a peek down here in what would be otherwise a func7 style field to figure out whether we're doing an arithmetic shift or a logical shift, okay? So in that regard, in my document here, I kind of separate these off and made them unique and different than the other I-types. That is very important when it comes to considering how you might represent this operand, this field, and treat this immediate value. If you're going to write, for example, a simulator or a disassembler or something like that in C or C++, because you have to make sure that you zero out all these extra bits over here in case there's a 1 hiding over there. It would mess with the shift amount number, okay? Plus, you have to look over here anyway to differentiate between the logical and arithmetic shifting. Now, when it comes to building hardware, and my point is, these really are all the same. Okay, the way you do that in hardware is you simply don't connect these other bits up to where they're going. All right, remember what happened over in our ALU here, the shift amount. We just physically hook up the least significant 5 bits of our immediate operand here. There's no extra hand waving going on. These are I-type instructions. We simply are ignoring all the other bits of that immediate operand. So where are we going with this? What's the notation I've chosen in here? Well, when we look at func3 of a shift right instruction, we don't know if it's arithmetic or logical unless we also look at what I'm going to call func7, even though, like I said, in this instruction, it's really just the bit number 30 over here. That is why I call this SRX. What we know is we're shifting right. If you see the opcode of 13 and the func3 is set to shift right, we don't yet know if it's arithmetic or logic until we look at bit 30. And if that bit 30 is high, in which case it must be, if it's an arithmetic shift, then we know that we're shifting arithmetically, okay? That's why this says, I don't care what it is over here because it doesn't have any effect on these instructions, but we do care here. And it must be high, and it is high. If you look very closely at the SRA instruction over here, see that 4 right there? That 4 has a 1 bit in bit number 30 over here. That's why this is high right here, okay? The fact that it's high in the context of these other ones means we're shifting right arithmetically. Everything else down here matches the other instructions. We have an RS1 value. It makes sense that it would be decoded and shown in here. In other words, we care about it versus don't care about it, okay? That's how we read all this fun stuff. The IMMX value in this case is 2 because that was the number of bit positions we want to shift, all right? So that's how that one is decoded. It's fetched and decoded, right? Again, we still see the addresses moving along and the address bus down here, right? And we see the instructions coming out of the memory, 4 bytes at a time. The last instruction in the sequence is a subtract instruction, and it makes, or rather the last 2 instructions, we have an add and a subtract. I did both of these on purpose, again, to show the func7 field has to be low for an add and high for a subtract. And again, to emphasize the fact that the opcode of the add and the subtract, these are both R-type instructions. All R-type instructions will have an opcode of 33. Okay? The add and subtract instructions both have the same exact func3 value. In fact, that func3 value for both of these is 0. All right? The 3 bits of 0. And it's not until you look at this func7 bit, the bit number 30, that you determine whether or not you're adding and subtracting, all right? Now, that, of course, is what goes into this sub-SRA input on the ALU here. If you look closely, it comes down and comes out of the finite state machine, all right? Most of the time, this block down here will simply propagate the instruction bit number 30 through itself and out over here, okay? Other times, it needs to use the ALU for other purposes, okay? So the ALU is not always directly under control of the instructions, okay? It is always under control of a finite state machine, okay? That can simply, if it wants to, let func3 and the sub and shift right arithmetic inputs signals just flow right through it, and other times it won't, and we'll see that as we look at some of these other timing diagrams. So the rest of what's going on with add and subtract should match what we've seen so far. What do we got here? The only other thing, I guess, that's unique about it in contrast to the other ones is that we now have an RS2 field. The R-type instructions have an RS2 value. So RS1 is 2 and RS2 is 15 in the example of adding. This one here, I'm going to subtract what? The value of x2 from the value in x20, and I'm going to store that in x1. So again, x1 is the destination register, and we should down here see, again, for RS1 and RS2 in these 2 rows here, we see the 20 and the 2. We do not have an immediate operand in the R-type instructions, so we don't bother to pay attention to what might be on the IMMX bus, right? That's what this line down here represents. So this is how we can fetch and decode these instructions in the order in which they appear, using an adder circuit and a D-latch for the program counter, and a D-latch for the instruction register down here to grab onto the values as they come out of memory. So let's now move on to figure number 3 in this handout that I've got down here. Now I'm going to talk about fetching, decoding, and executing of the U, R, and I type instructions that we were just looking at, all right? So the only difference between what we just saw and this diagram here, as we scroll through this, is there's simply more showing. This timing diagram now shows every single bus and signal that's labeled in this schematic. So what happens over the course of time, not only to fetch these instructions and decode them, but also to execute them. Let's look at the Louis first. Remember, the Louis is going to try and put this value here into register 15. So the first thing we need to do is fetch it. Program counter is currently 0. We already looked at that. Program counter is sent down to the address bus of our memory because adder cell here is high, and that's why there's a little PC right there. And that's why the address is 0, and the value that comes back is the instruction for the Louis right there. And this 8 if you recall, is the actual part of the operand. So how then does the Louis have to work? Now let's look back at the schematic diagram here. How does the Louis work? Now remember, the Louis takes the immediate operand after it's been sign extended and zero extended by this circuit right here. And it wants to store that value into the RD register. Somehow we need to get the RD value up here from this bus down here. What is the data path that we need to do that? All right. We could actually start all the way back at the instruction. We know that the instruction comes out of the memory. We've talked about that before. The instruction register, once it has that instruction stored in it, the value of the encoded instruction flows through this box here that does the extraction of the bits based on the opcode. Sign extend, zero extend it, and flows it out over here. So once that happens, I can get it into the B bus, the ALU. I can get some of the bits, go down to the shift amount down here. Well, that's not useful for us because that's only going to be the 5 bits. We only use that for shifting. We're not going to shift in this instruction. So what are we going to do? What we need to do is get the immediate value to flow through the ALU, out the queue over here, around this way, up over here, through this mux, and then it can become available to store in the destination register. So how do we do that? Well, we could add 0 to it and let it flow around here if we wanted to. Or we can take our ALU and create more functions, right? Now, there's really no reason we couldn't alter the multiplexer that we know is inside this ALU as part of its output stage and make more inputs. Let it do more functions. No big deal, right? One of those functions could simply be B. Take the value on the B bus and send it out Q. If that's the case, the function here could be set to whatever code on this bus here represents set Q equal to B. When that happens, B would flow out over here and become part of the inputs to this mux here. And as long as the RD cell bus had what? Was set to 1, right? Input number 1 here. Then it would flow up and around here and become able to be stored in the register file, okay? Of course, RD would have to be set to the destination register for that to work. Once all that's done and the data arrives over there, we have a rising edge on this read clock field right here. And we'd be done. All right, so back in our timing diagram, what do we see? Well, the ALU function, rather than showing the bit encodings, I just put the function in here. Do whatever's necessary on the function bus to make Q equal to B. The ALU B select at that time is high. And I add a little note in here to remind us that ALUB, the multiplexer that chooses what goes on the B bus, the ALU, when it is high, it will present the value from IMMX. When it's low, of course, it's RS2. But right now, it moves high because we're executing a Louis. And the control box in the lower right-hand corner of our schematic would know that when it sees an opcode for a Louis, it's supposed to move the ALUB select output from the control unit to high, right? It'll also move ALUA select to where it might need to be, but in this particular case, we don't even care, right? Because if Q equals B, we don't even care what's on the A bus. All right, and that's what this gray box here shows. There's no RS2 value, there's no RS1 value, so no matter what may or may not be on those buses is utterly irrelevant, okay? So once we know that Q equals B, the output of the ALU will be simply set to whatever the input is, okay? And because of this signal here, we know the input is going to be that value there, okay? Once this is coming out of the ALU, and we know that our D select is set to 1, like we just saw in the schematic, and I remind myself while talking that that is the value for the ALU to go through that multiplexer, okay? Then on this rising edge right here, the value on the RD bus, which is given here, which is this value right there, is going to be stored into register 15. And at that point right here, with the rising edge of this clock right here, we've just finished doing whatever it takes to do Louis X15, comma 8. The latter half of this instruction cycle, as I mentioned before, is dedicated to dealing with advancing the program counter. Because remember, in the RISC-V, we advance the program counter at the end of the instruction. That has to happen somewhere, and it takes a certain amount of time. So we do that in the latter half of the instruction phase, okay? You can see that we go from 0 to 4 here. And that 4, as I mentioned earlier, goes down to the address for the memory bus, and the memory output reflects the value of that new address, right? And again, on the rising edge, what we'll see happens at time T3, the instruction register is then loaded again. From here, it ends up getting loaded in the instruction register for the next 2 clock periods, during which we will execute our OWI-PC function. Now remember, OWI-PC and Louis are basically identical in every way except OWI-PC, rather than simply propagating the immediate value, in this case it was 8, around and storing it into RD, will the OWI-PC, on the other hand, will take the immediate value from here and add it to the current program counter value, and then send that around to the RD register. So we should see a very similar situation going on here. First of all, we see this weirdness going on here. We'll come back to that in a minute. The RD register here, X2 is 2, so we would expect to see the RD field set to 2. We know the RD cell ALU has to get the value from the ALU into the register file. And we know that once the value we want is available on the RD val bus over here, we have to see the rising edge of the clock that stores the value into the register file here, okay? Ultimately, we're going to see this is the value that needs to get stored there, but let's see what's going on. Why are these things doing this? We'll come back to that in a minute. Program counter is already does what we've discussed before, no big deal. This is the current instruction that's executing, okay? We don't have an RS1 field, we don't have an RS2 field, none of that matters. Look what changes down here. Remember, the only difference between a Louis and the OWI-PC is whether we just take the B bus, which is sending through the value of the IMM operand, and change ourselves around to, rather than doing that, we're going to simply add the IMM to the program counter, all right? So remember, ALU A select, the MUX on the left in our schematic over here, allows me to select between the program counter and RS1. This instruction has no RS1. So we set ALU A select to 1, and we want B select to be set to 1 as well. And that'll put program counter here, the immediate value there. I can tell the ALU to then start adding the function here and make sure that sub SRA is 0, so that it's adding rather than subtracting, at which point the Q here in this case would be program counter plus immediate, rather than just the immediate value. Now we see exactly that is what's happening here. ALU A select now matters. It didn't matter here because we didn't even use the A bus on the ALU. Now we do. So we have A plus B, okay, is what we're setting the function to. Sub SRA didn't matter at all over here, because if we're just propagating B through, who cares, right? Now, sub SRA has to be low in order to add, and we talked about this at great length earlier on in the course, okay? So if we say A plus B, and the A bus has the program counter value on it, and the B bus has the immediate value, then the sum coming out of the ALU will be this value here. The program counter currently has a 4 in it, right? Because that's what the program counter has right there. It's got a 4. And the immediate value is the 1, 2, 3, 4, 5 with the 3 zeros, the sign extended and 0 extended value of the immediate operand in this OWI-PC instruction right here, okay? Now, why this? Okay, now remember what the ALU was doing. It's adding this immediate value to the current value in the program counter. Well, during this time period here, the program counter has a 4 in it. So the sum is exactly this, 1, 2, 3, 4, 5, 0, 0, 4. And the immediate value doesn't change. Nothing here changes. But the program counter changes right here from 4 to 8 to get ready for the next instruction. So what happens is the value that's coming out of the ALU here is the answer we want. Remember, OAPC adds current constant of the program counter to the immediate value. The program counter is equal to the address of the currently executing instruction at that time, which is 4. When we get to the advanced phase, the program counter goes over to 8. So, and of course, the ALU sees the input change from the program counter register, and it reacts by calculating a new sum. So we need to make sure that this sum is what gets stored in the RD register and not the one over here. And we talked about all this before, and when we talked about finite state machines and the speed of light and everything else, as long as this value is valid at the time that we see the rising edge right here of the destination register clock signal, we're gold. And it is. The RD val here is what we want, and we clock it into the RD register number 2. We immediately pull the rug out from under its feet, but we don't care because that happens after this rising edge. How do we know it's after? Because we know that the PC clock rising edge happens at the same time as the RD clock rising edge. And it takes time for the program counter latch to change from 4 to 8. That's why these X's are stretched out like this. It says time is passing in here. And we also know that the 8 here in the program counter takes time to flow into and through and out of the ALU, in addition to all the other stuff, that the time that we wasted getting it through the latch. So by the time this value here changes from the 4 to the 8 in, quantum physics time, an eon has passed, and we know that this value here will have been safely stored into register 2 on this rising clock. Okay, so that's how OAPC works. Add immediate. You'll see a lot of common theme in here. We already talked a little bit how, OAPC doesn't have a func3, and it doesn't care about whether it's adding or subtracting. This is where the SRA field, as I mentioned earlier in the schematic that comes out of this control block, has to be under the control of the control block and not just the instruction. Same with the func3. Sometimes the finite state machine down here needs to manipulate the ALU in ways that are independent of the way that the current instruction might be encoded. Otherwise, that's why we don't just take this func and connect it directly to func3. And that's why we don't take the sub and SRA field and just directly connect it to the bit number 30 of the instruction over here, okay? We don't do that because sometimes we need to use the ALU for reasons other than what is immediately apparent in the instruction itself. When it comes to the add immediate instruction, the func3 field does matter, because all the I-type instructions have the same opcode. We mentioned that before. Sometimes the func3 says, I got an I-type that is an add, other I got an I-type that's shift right, and so on. We already looked at those guys, okay? So what happens for this add immediate? We have a destination register of X1, we have a source register 1 of X2, and we have an immediate operand. So again, we saw this before, we see the source register has a number in it, and because I've added the extra fields in here, I can show that the RS1 value coming out of register 2 at this time is going to be that value. Why is it going to be that value? Because we just stored that value in register 2 over here. All right, so that's what we know. That will be the value coming out of the register store when RS1 is set to 2. What else do we know about this? We know that we're doing an add immediate operation, and in order to do that, we need to add the value of RS1 to the immediate operand. So we need to take ALU select and ALU B select and set them to the right values. And as I show right here, when ALU select is 0, remember that means propagate the value from RS1 into the A bus of the ALU. And when ALU B select is high, which has been so far all along, then the IMM value is propagated into the B input of the ALU. The ALU function under control of the finite state machine will be set to add A plus B. The sub and SRA field would have to be low in order to do an add versus a subtract. So again, the finite state machine will make that low. We do not have a bit 30 in this instruction, so that has to be done by the finite state machine itself. So then what happens here? We're doing an A plus B. That means we're adding RS1 plus IMMX. The output of the ALU is obviously then going to be the sum, right? We're adding 10 to whatever the 1, 2, 3, 4, 5, what was it, 04, right? That's the current value of register 2. This is the immediate value after it's been sign extended. The sum is this. That value there will propagate up and through the RD value bus because the RD select bus is still set to propagate the ALU into the register file. Remember, that is this mux over here. The RD cell controls this guy. And we're propagating the ALU signal up and around over there. And again, we show only the left half is relevant here because once we've clocked it in, it doesn't matter anymore. It can change. The main reason I wanted to show this left and right was because in some cases it does change when it doesn't matter. Okay? So that's the add immediate. You can imagine the shift right arithmetic immediate, all these other ones. It's just more and more of the same. When we want to shift it right arithmetic, we do now have a bit in the instruction bit number 30 over here that tells us whether it's supposed to be arithmetic or logical. And we propagate that bit into the ALU down here, okay? We get it out of the instruction down here, bit 30. This state machine propagates it up and through to the ALU up there. So in order to be arithmetic, it has to be high. Otherwise, the ALU would not shift it while extending the sign bit to the right to do an arithmetic shift, okay? What happens down here? The usual stuff. The destination register X20 right there, okay? We should have an RS1 of 15, and the shift amount should be 2. Then we talked about that before. The only difference now is we show you the value of register 15 because I've added these extra lines to this table here. Current value in X15 must be that because that's what we stored in X15 when we did the Louis earlier, and we never changed it since then, okay? So what happens to the ALU? What is it doing at this time? Well, we said they function to say, look, I want you to shift A to the right, however many bits is in the shift amount input. And the SRA and sub bit is set to high, which means I want to shift arithmetically. We don't really care what's on this B select input at this time. This really doesn't matter right here. I probably should have put a gray bar in here. It really doesn't make any difference, right? Why? Because it's shifting the input on the A bus to the right. It's not even looking at RS2 at this time. So it's critical that the A select up here does have RS1 selected so that the value of RS1 is sent to the A input on the ALU. The shift amount is the value that comes from the immediate operand, which we drew like this. Remember, the IMMX, the bottom 5 bits for RV32I represent how much we're going to shift if and when we need to shift. Therefore, if the function of the ALU is to shift A to the right, arithmetically, based on whatever number is in the shift amount, it will output that value on the output of the ALU, which is down here. Now we show IMMX is currently set to 2, because that's what happens when the shift amount is 2, right? The ALU shifting, what is it doing? It's shifting the value of, is it just X15? Yeah, X15 right here. Oops. This 8,000 there shifted right to E, and I see the answer is wrong. I need to fix my handout here. And with the magic of editing, voila, it's fixed, all right? If I take the hex value 8000 and I shift it right 2, I'm going to get 2000, okay? And that should be obvious. I hope you can do that one in your head. If you shift 8 right to the right once, you end up with 4. And you shift it again, you end up with 2. You're really dividing it by 2 every time you shift it right one place, right? Okay, so this value down here coming out of the ALU propagates up and around. I did put the right value up here into the destination register on the rising edge of this clock signal here to store it in the register file. So that leaves us with the add and subtract instructions. These are both R instructions. These do not have an immediate value. They have an RD register, which is, in this case is X1, and has an RS1 value, which is X2, and an RS2 value, which is X15. For this instruction here, the subtract stores the difference in the X1. Its RS1 value is at 20, and the RS2 value is at X2. Over here, these instructions are the same in every way, shape, or form, except, as you already know, rather than having the function 7-bit in bit number 30 over here of the instruction being low for an add, it's high for the subtract, because that thing controls whether we're going to complement the subtrahend in order to do a subtraction. All right. So if you look at everything that's going on down here, all the clock cycles, and it has a, an RS1 value is on this line here. Let me shrink this down so we get it all on the screen at once. They both have an RS1 field and they have values. They both have an RS2 field and they have values like this down here. Okay. The ALU is adding in both cases, except this signal here goes high in order to complement the subtrahend. Okay. The output of the ALU down here in the sum is propagated into the RD register. Again, the RD select has been set to ALU this whole time. And on the rising edge, the sum here gets propagated into and stored into register 1. Down here, the difference would be stored into register 1 on the rising edge here. Okay? And all the while this is going on, the program counter keeps ticking away to the next address, the next address, the next address. And because we're always sending it down to the memory, as indicated by this signal here never changing, this is the address that goes into the memory. You just simply see the memory always outputting the current instruction value as it goes. Never once have we written anything to memory, so none of this matters. This is actually used for reading from the memory, rather I should say. But we've never written anything into the memory either. Not for these instructions. Thanks for watching. See you next time.